Swayam Prabha. Digital India. Educated India.
Hello, welcome back again. So we are discussing metals in biology, right? I think you got a sense that metal has a role in biology, right? Well, just to remind you, more than 50% of our body weight is metal. So I think it is not just there just to be there, it is playing a role. Right. Let us see some more exciting chemistry. Okay. So, today we will discuss mononuclear non-heme iron enzymes. Okay. You have seen some of it before, but let us see a larger picture than what we have seen before. Well, as the name suggests, this is mononuclear, that means one nucleus, I guess, one center, one iron center, one center. Mononuclear. Non-heme means there is no heme involved, no porphyrin involved. Iron is iron, NHI, non-heme iron enzymes. So, the enzymes where you have one iron center and non-heme one, okay, which whatever is not porphyrin we usually call that as non-heme. Okay. Porphyrin iron is not there, so it would be called non-heme iron, okay, and it is mononuclear. One metal center would be there, or one non-heme iron center will be there, okay, fine. Well, the role of these enzymes are very simple, or rather complex, or rather interesting, okay, and that is it can couple oxygen oxidation to substrate oxidation. So, that is the organic chemistry, synthetic chemistry, absolutely synthetic chemistry. Its nature is I think there is nothing stopping in saying that it is the best chemist ever. Nature is ever best in everything, and that can do, nature can do substrate oxidation, okay, better than any synthetic chemist can imagine, okay. Hydroxylation precisely done, wherever you want done. Epoxidation effectively, whatever olefin need to be epoxide, from epoxide can be done. Ring closing, you asked, nature did it. Desaturation, absolutely perfect. So, there are many other reactions, this is just a short list. There are many reactions, ND alkylation done, sulfoxidation done, whatever you need. Of course, you may not need it, but if you want to do it by using enzyme, it can be done, okay. So, these non-heme iron enzymes are coupling oxygen oxidation to substrate, that means substrate is also getting oxidized. Not necessarily always oxygen has to get in, okay. Some cases oxygen is getting in, some cases there is no oxygen involved into the substrate, right, or in the mechanism yes, but in the final product there is no oxygen is getting incorporated. So, there are two different type of non-heme iron enzyme one can think of. One is oxygenases, which will end up incorporating oxygen atom from oxygen into the product. So, you start with a organic substrate, you get a product, oxygen atom is inserted into that product. N number of, it could be 1 oxygen atom, 2 oxygen atoms and so on. Substrate to product will have at least one more oxygen atom incorporated. On the other hand, these are of course these are oxygenase enzyme. On the other hand, there are oxidases where you have a substrate, but in the product there is no oxygen atom incorporated. Okay. So, these are called oxidases, but of course still oxidation is going on in the product. It could be ring closing, desaturation and some other things happening, but overall as you will see some of it in a moment, that these are catalysts, these are non-heme iron enzymes are catalyst for many reactions, just like what we have seen in case of the heme. It can participate in DNA repair by involving themselves in these oxidation processes, and antibiotic biosynthesis, collagen and many other things. Okay. Their reach is really far. Okay. And also it utilizes, quite interestingly, high valent iron oxo intermediate. Of course, the nature of these species may vary, the ligand may vary, but overall it is a high valent iron oxo species that is at play, which is a very reactive intermediate, and that is why perhaps nature has chosen high valent iron oxo intermediate to be the reactive intermediate for a number of oxidation reactions, right. Alright, let us try to see a little bit of the chemistry that these guys are capable of doing. So, we are trying to see the reaction that is proposed or believed or now kind of proved to be mediated by high valent iron oxo intermediate. High valent means usually it is iron 4 oxo, if not iron 5 oxo. Okay. Iron 4 and iron 5 oxo. So, as you can see over here, let us say this is a iron 4 oxo, this is a representative example, you can read really this nice accounts. So, iron 4 oxo with some other ligand attached with it, iron 4 oxo, iron 5 oxo hydroxo. So, these are the different types of species one can think of forming in the context of non-heme iron enzyme. Okay. These are the reactive species, these are the truly reactive species. Okay. So, for instance, if you are looking for a hydroxylation reaction, it could be aliphatic substrate, right. So, these are the dream reaction, we have seen this, right. So, these are the dream reaction. In a sense, synthetic chemist cannot really do these reactions that very efficiently. I mean little bit, but not really that great at all, I mean nowhere close to be great. So, this hydroxylation reaction by nature can be done in a predictably selective manner, in an efficient manner. Things are really excellent and it is going on beautifully, right. So, we will have this iron 3 hydroxo species formation, and from there of course you start with iron 4 oxo, react with RH to abstract hydrogen atom from the RH to give you R dot and iron 3 hydroxo intermediate. Now, this hydroxo can undergo rebound to facilitate this R dot to ROH formation. So, overall you started with a high valent iron oxo intermediate, reacted it with a organic substrate such as aliphatic substrate, aliphatic sp3 CH bond can be hydroxylated through this mechanism. Okay. Of course, there is a twist, very interesting twist in this mechanism, and that is this iron 4 oxo, if there is another ligand such as halide, let us say chloride. Okay. Now, these halogen can also participate provided this RH is perfectly positioned. Well, this is a chemistry which is quite fascinating, I would say. Still it utilizes iron 4 oxo to abstract a hydrogen atom to give R dot and OH, iron 3 OH is formed along with R dot. This R dot and this OH will combine with each other in other scenario as you have seen over there, but in this case if this R dot is positioned very closely with respect to this halogen or halide, chlorine, let us say chloride. Now, this chloride will end up reacting with this R dot, of course in a radical fashion to give the Rx species. So, this is actually a page out of this chemistry, but then there is enough twist into it to provide further these Rx and iron 2 hydroxy. That is I think quite phenomenal. Okay. Now, so this is oxidative ligand transfer. There is going to be another interesting avenue where you will see that this RH, which is a part of the substrate, can be abstracted, or the CH bond can be abstracted with iron 4 oxo to give R dot radical. Now this R dot radical and this RH, which is again inside the ligand backbone, CH bond can be cleaved to undergo CC bond formation. That means a cyclization reaction can occur. Of course, you can have desaturation, another adjacent bond or carbon hydrogen bond can undergo radical formation, and a double bond olefin formation can be possible. So these chemistry, either cyclization and desaturation will be possible. So as you see that the same species iron 4 oxo, it is taking part in all these beautiful chemistry and simple yet effective chemistry, right. So you see substrate hydroxylation. In this case, substrate hydroxylation is absolutely prevented, only selective halogenation or ligand transfer is happening. So hydroxylation is a possibility, still it is not happening. So the design is such that, strategy is such that it is selectively, of course the oxidation potential will also play a role, but still most importantly the positioning of the substrate is the key, which is essentially pushing for the halogenation reaction. Okay. In this case, the substrate hydroxylation has to be prevented. R dot is forming, of course you can immediately think of ROH formation just like here, but that is not happening. You see a cyclization which is perhaps more likely to be happening rather than the hydroxylation reaction. So diverting this pathway is always going to be difficult, right. So always there is a tendency for this hydroxylated product formation, but as you have seen in this case, as also in this case, it is possible with a suitable substrate and the right orientation, it is possible to undergo or force them indirectly to pick up pathways, to pick up some other possible product formation. Okay. So it could be desaturation or cyclization. Another fascinating aspects of these high valent iron oxo intermediate is these are electrophilic in nature. So this is a nucleophile, a benzene ring, a nucleophile can attack on this. So electrophilic aromatic substitution type of reaction can occur, as you have seen the Wheeler type of intermediate is forming, and you can end up getting the hydroxylated form of this benzene ring, right. So essentially benzene to phenol is forming. So these are electrophilic aromatic substitution type of reaction. All this is not all, there is yet another fascinating aspect, that the cis dihydroxylation chemistry. If you take even a benzene ring, it is possible to have these non-heme iron enzymes set up where it is a iron oxo hydroxo species is the key intermediate, where you see the cis dihydroxylation of this olefin-nic double bond is taking place. Well, that is getting quite exciting, right. Are you not excited? I am quite excited, right. This is like absolutely complete range of synthetic chemistry you can see, right. You ask a synthetic chemist, anyone like us, to do this chemistry in a very effective manner, I think it is going to be challenging. I mean in synthetic setup we are not that smart yet, right. What nature has done is unbelievable. I mean complete control, no problem whatsoever, do the chemistry that is required or thought of absolutely perfectly. The catalyst turnover number is absolutely brilliant, selectivity is perfect, and it is like whatever you want, it is like toying with the substrate. You see all of them are having similar substrate, but the outcome is completely different, right. So I think we need to go a long way. Synthetic chemist has to learn quick or has to fight for decades and centuries if ever we get anywhere closer to what nature does and how beautifully it is done. Okay. I think one way to perhaps do this chemistry is to do biocatalysis or enzyme catalysis, or try to do synthetic chemistry which is as closely mimicking those enzyme as possible, but that is going to be extremely expensive and extremely time consuming to design what nature does in the catalytic domain or in the metalloenzyme cases, right. These are beautiful metalloenzymes. So, the fight will still be on, fight will always be there to get closer to the nature, right, to do what nature does, right. Well, let us move on and see one of these cases. I think it is a fascinating case, and I think this is something you may not have seen something before, and that is this alpha Kg dependent dioxygenase. So, there is a organic substrate which is utilized in the process to extract out substrate hydroxylation chemistry or other ligand transfer chemistry such as halogenation reaction. Okay. This is a very I think exciting enzyme. These are having 2 histidine and 1 aspartate, a facial triad motif, as you see 2 histidine and 1 aspartate and 3 water molecules are there. So, these are quite interesting compound. This alpha Kg, alpha ketoglutarate. So, this is alpha ketoglutarate, you know the glutamic acid. So, alpha position of it is keto. So, this is whole is alpha ketoglutarate. This alpha ketoglutarate is bound with iron center in a bidentate fashion. This is now a bidentate ligand. 2 of the water molecule has gone out from this coordination sphere of iron, and you have seen that alpha ketoglutarate has come in. Fantastic. It is a iron 2 plus. What do you expect? That is going to be even beautiful, because now you have a organic substrate attached to it, 2 histidine, 1 aspartate and 1 water molecule, and then the real substrate, this is the dummy substrate, this is required for its activity, right, absolutely essential. But this is not our target substrate is something else. It could be completely aliphatic CH bond containing substrate, it is a sp3 CH bond containing substrate. These are the most difficult substrate. Usually bond dissociation energy for these are 104 or 100 plus kcal per mole. So, this is pretty difficult bond to break, and nature has mastered it like completely. I mean, got it right, absolutely got it right. So, that is you will see in a moment that this RH which is appended right in front of this active site, right. So, you have 2 histidine, 1 aspartate and alpha ketoglutarate is appended beautifully right over there, and RH is just hanging on there. It is on a support, there is a substrate binding pocket that is holding it right in front of it. Now, you have oxygen, it gets activated, okay. Iron 3 plus is forming, and this you have the superoxo, right. One of the electron from iron 2 plus is given or delivered to the oxygen to give you iron 3 superoxo. Well, fantastic, right over here, reduced species, oxygen, iron 3 plus, superoxo. Iron 3 superoxo is forming. Now, this iron 3 superoxo can react with this alpha ketoglutarate, because this is an intramolecular substrate already ligated with iron, perfectly placed. It cannot easily react with this one, because this is a easy substrate for the superoxo to attack. So, this iron 3 superoxo will now then attack to this alpha keto center, forming a peroxo like intermediate, beautiful intermediate. As you see, this is a 5-membered ring formation is happening, and this is very much fast. This is very fast compared to the hydrogen atom abstraction from the aliphatic substrate. That is not going to happen that easily anyway, this is very difficult. Now, so superoxo may not be that active to pick up the CH bond of an aliphatic substrate. Subsequently, as you see, the oxygen bond cleavage of this so called alkyl peroxo. This is the now whole alkyl group and this is now a peroxo group, if you may wish to call it peroxo. Now of course in the process when it is attacking, it's going to be 1 electron oxidation further to make it a O minus. So iron 3 is now becoming iron 4. Iron has given 1 electron to the oxygen, so upon abstracting. So if you are thinking a radical mechanism, it is a radical O dot over here, it attacks over there. So it forms a bond, homolytic cleavage of this CO bond if you are just following stepwise. So this bond is formed, O dot is formed, O dot need to be O minus, that electron is coming from iron and that is why it is iron 4. Right. So this species is forming really beautifully and simply. Subsequently you will see that oxygen bond cleavage to give you this succinate upon removal of carbon dioxide. So removal of carbon dioxide happen over here, you end up cleaving this oxygen bond and you form a CO double bond here, CO double bond, and this O is remained bound with the iron. Nothing happened to the oxidation states of the iron, this remains 4+ from here, this oxygen bond cleavage happening. Overall this iron 4 oxo then is formed. Now this iron 4 oxo is capable of abstracting hydrogen atom from the substrate, more so because the substrate is positioned right over there, right in front of the iron 4 oxo species, right. That is fascinating, right. So you have an iron 4 oxo sitting and you have a substrate sitting. This is a highly reactive intermediate. Now they have almost no chance of doing some other adventurous thing. It was alpha ketoglutarate which was ready to be there and very active substrate, it was therefore attacking that. But in presence of organic substrate at this point, when you have a iron 4 oxo, it is not going to pick up on anything else at this point since the substrate is there. If the substrate is not there, that is a different ball game, we will discuss some time later. Now this since the substrate is there, it perfectly matches everything, so it will go on in abstracting hydrogen atom from this CH bond and then iron 3 hydroxy. If you are cleaving it homolytically, this become iron 3 and O dot picks up H. So OH is formed and then this cleavage, 1 electron here, another electron there. So 1 electron H dot comes over here and then R dot goes right over there in the binding pocket to the close vicinity of OH with not too much released from this, you can say that it is solvent cage. Now immediately it reverts back. This is what is known as rebound mechanism. Hydroxo rebinds with this R dot to give you ROH, right. So this iron 2+ is regenerated. If you are looking at, if you are once again cleaving homolytically, iron 2 dot and OH dot, this OH dot and this R dot combines to give you ROH and the catalytic cycle goes on beautifully. So what you have seen so far? You have seen that it is possible to manipulate, I would say, the chemistry. You have seen in the last slide, manipulation can happen based on what type of organic substrate is there, of course also what type of iron oxo species is there. It is most often it is a iron 4 oxo species, but in some cases it could be iron 4 oxo appended or attached with some other ligand, right. That is going to be quite exciting, right. In other cases it could be iron 4 oxo, instead of iron 4 oxo it is a iron 5 oxo hydroxy. Now these are the chemistry happening. A moment ago we were just discussing this chemistry, substrate hydroxylation chemistry done by a very effective setup, that is alpha ketoglutarate dependent enzyme, right. We did not discuss much of this yet, we will discuss this in the next class. Let us look at this chemistry, hydroxylation chemistry once again very quickly. So this is alpha ketoglutarate dependent chemistry. Without alpha ketoglutarate this enzyme does not work really Well, so we have to have this alpha ketoglutarate over there, and that is because it facilitates overall this iron 4 oxo formation rather easily without anything else from outside, right. So, alpha ketoglutarate is a sacrificial substrate, you can say. In this case it forms alpha ketoglutarate to succinate. Alpha ketoglutarate is overall forming succinic acid or succinate, as you can see over there, and in each and every step it has complete control, right. So, initially it is a iron 2 to iron 2 formation and then substrate orientation. Oxygen reacts with iron 2 to give 1 electron transfer to form iron 3 plus and superoxo. This superoxo radical then attack on the alpha ketoglutarate to give you iron 4 peroxo alkyl peroxo intermediate, which undergoes cleavage to give you iron 4 oxo. It is a radical, I mean, it is one way to do is think of it as a radical mechanism, then things becomes much clear to understand. So, it will abstract a hydrogen atom from here. So, R dot remained, hydrogen atom comes in. So, that leads to the oxygen bond cleavage, iron 3 hydroxo, and then OH and R dot combines to give you R dot iron 3 hydroxo and hydroxo radical transfer and iron 2 reforms. So, this is how things are happening, and that is beautiful. In the next class we will be discussing the alpha ketoglutarate dependent halogenase. Okay. These are hydroxylases or hydroxylation chemistry you have seen. In the next class we will discuss almost same mechanism, but with a twist. Okay. Twist is in the ligand that is associated with the iron center. Instead of these 2 histidine 1 aspartate, one of it will go out. Okay. We will see that in the next class. Keep studying alpha ketoglutarate dependent dioxygenase and other enzymes and the beautiful oxygenation and oxidases chemistry by the non-heme iron enzymes. Okay. See you next time, till then, bye bye.